In this video, we'll talk about the Diels Alder reaction. So the first reaction we're really focusing on in our class. I have a little bit of history about this reaction and the importance of the Diels Alder reaction. I don't necessarily expect you all to have this recorded in your notes as far as the history of the reaction and why this is important, so you can kind of sit back and listen for a minute or two. This reaction was discovered by German chemists Otto Diels and Kurt Alder in 1928, and it won the Nobel Prize in 1950. You see the picture here of those two chemists. Kurt Alder was actually a student of Otto Diels at one time. This reaction is still very widely used, and I actually have an article linked into this week's folder on Top Hat, so you can look through the article if you want to see the many different ways the Diels Alder reaction is used still today. Or you could even just do a quick Google search and you'll see the many different applications of this reaction. Some of the ways it's used is to create rubbers and plastics. It's used in the production of synthetic steroids. It's used in nanotechnology. And last I checked, scientists were looking into using this reaction in producing polymers to be used for drug delivery. This reaction is very widely used and important in the field of chemistry because it produces a high yield of product. So for a lot of the reactions that are put into the reaction, you get out a high yield of the desired product, and a metal catalyst is not required. For a lot of carbon-to-carbon bond creating reactions, a metal catalyst is required, and we'll certainly talk about those types of reactions this semester. But the Diels Alder reaction is special in that it doesn't require a metal catalyst, so it's a simpler reaction to carry through. So let's look at the reaction scheme and an example of a Diels Alder reaction between two molecules. We've learned about dienes so far, and you probably are not surprised to hear that dienes are used in Diels Alder reactions. So let's draw just a simple diene. This is the cis conformation of 1,3-butadiene. So this is our diene. So that's one of the reagents that's used in the reaction. The other reagent we call a dienophile. And the dienophile is a molecule that has another carbon-to-carbon pi bond. It can be a double bond or a triple bond. In this molecule, we'll look at double bonds. And then other groups are bonded to those carbons. So it's not a diene, but it does have a pi bond. I will keep these groups as general R groups. So it could be a longer carbon chain, it could be two more hydrogens, it could be a nitrile group. We'll see a bunch of different examples. This molecule that's added here is called a dienophile. The suffix "phile" implies that this molecule or this substance is attracted to a diene, the first part of the name. So we've seen phile when we talk about nucleophiles and electrophiles in Organic Chemistry 1. A dienophile is a molecule that's attracted to a diene. When these two types of molecules react, so a diene and a dienophile, usually under some amount of heat, the product is a ring. So we take I'll just draw out the product and then we'll trace the atoms back to the reagents so we can see where each atom is now in the product. Okay, so here's the product from the diene and dienophile that we added. Two things about this reaction. One is that we call this a cycloaddition reaction. And that's because it forms a ring. Another way to describe this is 1,4 addition. And that's because the dienophile adds to carbon 1 and carbon 4 on the diene. Okay, let's look back to the reagents and the product now. We can trace, I'll use highlighting to trace the atoms that are part of the diene. So we have all of these atoms, I'm going to highlight them in orange. And where they end up in the product is how I've drawn it on the left side of the ring. So these are carbons 2 and 3. Here's carbon 4 with its 2 hydrogens. Here's carbon 1 with its 2 hydrogens. And then the hydrogens on carbons 2 and 3. So we can say this is C1, 2, 3, and 4. This is C1, 2, 3, and 4 on the diene. Now the dienophile, we have 2 carbons bonded to each other, each carbon bonded to an R group and a hydrogen. Here we have that part of the molecule now in the product. So the dienophile adds, there's a new bond from the dienophile to carbon 1 of, look right here, carbon 1 of the diene and carbon 4 of the diene. So that's why we call it 1,4 addition. And we create that new 6-membered ring using the atoms from the diene and the atoms from the dienophile. So this is the reaction scheme that overviews what's occurring in the reaction, just the reactants and the products. Let's now write out a mechanism so we can really understand where electrons are flowing and how these new bonds are being created. Going to draw the same diene and dienophile. I'm going to use different colors to show where different bonds are being formed. And really what occurs in this Diels Alder reaction is a shifting of all of the pi electrons. So one of the double bonds in the diene, I'm going to choose the top one, will form a new bond to one of the carbons in the dienophile. Those pi electrons can donate to that carbon, and that creates a new single bond between the carbon on the end of the diene and one in the dienophile. Now that would produce too many bonds to the dienophile carbon, and so the pi electrons on the dienophile will create a new bond to carbon 1 of the diene. Let me number these. And then lastly, the pi bond in the diene between carbons 1 and 2 will shift to produce a pi bond between carbons 2 and 3. And so now the product here, we still have, I'm going to write in black all of the bonds that did not change. Now the green arrow on the left shows a new bond forming between carbon 4 of the diene and one of the carbons in the dienophile. So that green line now that I drew on the right is that new bond that's formed. The blue arrow indicates there's a new bond formed between the dienophile and carbon 1 on the diene. So now I've drawn that in blue. And the pink arrow shows that new pi bond between carbons 2 and 3 on the diene. And so this is that cyclic product that we have for the Diels Alder reaction. We also call this reaction concerted, which means it's a one-step reaction. In future videos, we'll talk about different R groups on dienes and dienophiles and how to predict which R groups are going to influence the reaction in different ways. But this is the simplest mechanism to describe the Diels Alder reaction.